So let's start for the afternoon. So before, I will not introduce the next keynote speaker, but I will introduce the speaker who will introduce the next keynote speaker. Because they will co-chair the afternoon session about robustness and uncertainty quantification. So so Sébastien will be a co-chair with Aditya, and Aditya will be keynote also. So Sébastien is a researcher at IRT Saint Exupéry in the DEAL project also, specialized in uncertainty quantification. He has a lot of other specialties. And he's also a researcher at IMT, Institut de Mathématiques de Toulouse. So Sébastien, I leave you the floor for introducing Aditya.
Thank you, Gregory. Hello, everyone. So next, we have the pleasure to have a keynote by Aaditya Ramdas. So Aaditya is an assistant professor at CMU, Carnegie Mellon University, the Department of Statistics and Machine Learning. He was a postdoc at UC Berkeley before that, and prior to that, did a PhD at CMU, receiving a Umesh Gavekar Memorial Physics Award. So Aditya has got several grants and awards, COPSS Emerging Leader Award, the Bernoulli New Researcher Award, just to name a few. And his current research interests are in both theory and methodology. And they include, they are mainly in selective and simultaneous inference, game theoretic statistics, distribution-free black box predictive inference that you will hear about today. And in his applied interests include privacy, neuroscience, genetics, and auditing. So Aditya, thank you again for accepting to give a talk, and the floor is yours.
Thank you very much, Sebastian. And let me know if you can hear me and see the slides and everything's okay.
Yeah, we can hear you.
Okay, perfect. Thanks. Okay, so thank you very much for the introduction, for the invitation, and thanks all of you for being there. I wish I could be in Toulouse. I've visited Toulouse before twice, actually, even to the Airbus factory in 2008. And I love the city, but unfortunately, I have a 6.5-month-old baby right now, and travel is very tricky. So I'm happy to be able to give this online, and I hope you'll take my apologies for not being there in person. So today I'm going to tell you about something called distribution-free uncertainty quantification. And what are we quantifying the uncertainty of? We are quantifying the uncertainty of machine learning prediction methods, and typically black box ML prediction methods. And we want to be able to do so even if the distribution of the data is drifting and shifting. So those are the three themes in my title. So as we go along, I'll explain what we mean by this term distribution-free UQ. Black box ML prediction methods, hopefully everybody knows. And then how to incorporate robustness to distribution shifts and drifts will be a key aspect that comes in. Okay, so this talk is roughly going to be in two parts. I may not finish the full talk, especially the second half. Maybe I won't because of time reasons. That's not a problem. Hopefully you'll at least get a glimpse of both the pieces of the talk. So the first part of the talk will be on something called non-exchangeable conformal prediction, which is the first column. And the setting to which it applies is actually any regression or classification problem, maybe even with distribution shift and drift. The form of uncertainty quantification it provides prediction sets. It tries to cover the true label with a set of labels. And the setting that, even though it applies very broadly in today's talk, just to keep things simple, I'll be talking about real valued regression. Now, the second part of the talk will introduce a method called online Platt scaling. This applies to actually any classification problem, including with shifts and drifts. And the form of uncertainty quantification is to provide calibrated probability. So instead of providing a set of labels that covers the true label, here we're trying to probabilistic uncertainty quantification by calibration. And for today's talk, to keep things simple, I'll just talk about how it applies to binary classification. Okay, so maybe the first even 20-25 minutes will be on conformal prediction, and then I'll try to at least spend 10-15 minutes at the end on Platt scaling, but we'll see how it goes. So let's start with the first part. So this is the title of our recent paper of ours published in the Annals of Statistics this year, which is conformal prediction beyond exchangeability. And the idea of this I don't expect most people to know what conformal prediction is, and I'll tell you what that is. But the beyond exchangeability was the new part, which is how do you extend it to non-exchangeable settings. And my collaborators from this part of the talk are Rina Feugl-Barber, Emmanuel Candes, and Ryan Tibshirani. We call ourselves the Baccarati group, and we have written several papers on conformal prediction together, but this is our most recent one. Okay, so here are the high-level takeaways before I get into the technical details. Now, standard conformal prediction, which is actually more than 20 years old, it's a powerful and general methodology for quantifying the prediction uncertainty for black box machine learning algorithms. So instead of making a point prediction, we'll make a set prediction, and conformal prediction will be a kind of a nice wrapper that can convert point predictions into set predictions. Standard conformal prediction needs only two assumptions. It needs the data to be exchangeable, and it needs the algorithm that you're using, the machine learning algorithm, to be symmetric in the data, which means it treats all data points equally. And what we will do, I will introduce standard conformal prediction first, but then what I'll do is I'll show you how we are able to fully remove these two assumptions. So we can handle non-exchangeable data and asymmetric algorithms. And so we strictly generalize both the algorithms and the guarantees of standard conformal prediction. And these new methods are especially promising when you have settings of distribution, drift, and shift. Okay, so I'll first now get into what is conformal prediction and so on. So what is prediction? Okay, here I just have a bag of training data, and just to set some notation state, I have, let's say, n training data points. X's are the covariates lying in a general covariate space. Y's are the labels. In this case, let's say we're doing real valued regression, so Y is just a scalar, and we have n training data points in a bag. So prediction is the following problem. I see a new point, xn plus 1, that's the red dot, that I've never seen before, and I need to predict its label. And usually I pick some kind of an algorithm, like random forests, or nearest neighbors, or deep nets, and I use this algorithm and I apply it to the training data, and it gives me a predictor. And a predictor is nothing but a mapping from x to y. And what is an algorithm? It's actually anything that takes in some number of data points and spits out a predictor. So the setup is very general, and everything I'm going to talk about applies to any algorithm. So literally the definition of an algorithm is satisfied by, you could even be doing least squares for small amounts of data and boosting for large amounts of data, and that's also a valid algorithm. So once I have my algorithm, I run it on my training data, I get a predictor. I use that predictor to make a point prediction. So A of xn plus 1 is my prediction for yn plus 1. Now, typically, we train our predictors to be good with, relative to mean squared error or something of that kind. But this talk is going to be talking about predictive inference, and predictive inference is the task of uncertainty quantification, quantifying the quality of those predictions through an uncertainty set, for example. So I'm interested in it, like, for example, a red ball around my prediction. I'm going to call that set CN, and I'm looking for a guarantee of the type that the unknown label yn plus 1 lies in my set Cn of xn plus 1 with probability at least 1 minus alpha. So it's a high probability set that contains yn plus 1. So obviously the set is a function of xn plus 1. I mean, for a different test data point, I'll produce a different prediction set, but it's also a function of all of the training data. So the Cn really represents that it's a function of the training data as well as xn plus 1. And so the question I'm going to be asking is, how do we construct such a set? Like, how do we construct these sets that contain the true label with high probability? But the key point is, I don't want to make any distributional assumptions about the data. So distribution free UQ means that this error guarantee that you're seeing in the last line, it actually holds for all joint distributions PXY and all algorithms script A. Well, for now, assuming i.i.d data, and I'll relax that i.i.d assumption later on. But the question is, even if I just, even with i.i.d data, the problem doesn't seem obvious, but, I have data from some, underlying joint distribution, and I don't know anything about that, joint distribution of the data except the n plus n, except the n labeled samples. And I have some algorithm, which could be really weird. And I need to quantify the uncertainty of my prediction on a new test point. Okay, so that's distribution-free uncertainty quant. That's the goal. So more formally, this was defined about 20 years ago. Given labeled data drawn i.i.d from PXY, given any black box machine learning algorithm A that to help predict y from x, and given an unseen test point xn plus 1 from the same distribution, the goal is to produce a set. Here I'm suppressing the subscript n. So just a set C of xn plus 1, which is a subset of the label space. In for example, in our talk today, it's going to be an interval. So I want to produce an interval such that the probability that yn plus 1 lies in this interval is at least 1 minus alpha. And the two remarks, as I mentioned before, is in this, what I'm going to present, the algorithm is, it actually needs to be in permutation invariant, or I'm just going to call that symmetric, which means that the labels of the data points don't really matter. I could have called point 1 as point 8 and point 4 as point 9 and whatever. The algorithm kind of does the same thing. And so most machine learning algorithms we have, like whether it's ordinary least squares or random forests, they treat the points exchangeably or symmetrically. So they really do fit this framework. And on the assumption of the on the data, it doesn't actually have to be i.i.d, but you can relax it to being exchangeable data. But I mean, for the rest of this talk, maybe it's simpler to just think of the i.i.d case for simplicity. So I'll first spend the next 10 minutes telling you how to solve this problem in the i.i.d case, and then I'll spend 5-10 minutes telling you how to generalize it to the distribution shift or drift case. So just visually, this is kind of what you should expect to see from conformal prediction. Here I have a univariate x, so like really simple so that you can visualize it. And x is, well, on the x-axis here, it's between 0 and 6. And y is on the y-axis. In this case, it's between -4 and 4. And all of the gray dots are the true data. Let's say that's the labeled data that we have access to. Now, the red curve you should think of as being the machine learning prediction. So I take all of these, gray dots, and I throw it into a machine learning algorithm. Let's say in this case it was some kind of spline regression or quadratic regression, kernel regression, something of that kind. And the model I get out predicts the red curve. And by that I mean that at each point x, you can throw it into the model and see what the prediction is, and maybe it predicts something of that kind. But we're not interested in just this machine learning prediction, which is the red curve. We're interested in these conformal prediction intervals, which are actually telling you that, well, if x is 4, for example, then y is likely to be between -2 and 1 with high probability. But if x is 1, for example, then y is likely to be between -1 and 2 with high probability. And so um, we want to know, how do we produce these pink prediction bands, which I'm just conformal prediction intervals. It's an interval because at each point it looks visually like a band, but what you should think of is that each test point x, it's an interval for y. And I would like this interval to cover y with high, the unknown y with high probability. Okay, so we're going to show you how to produce this, and actually the algorithm is very simple, which is why I'm introducing it in a broad audience talk. Okay, so here's the idea. It's super simple. It's called, I'm going to show you split conformal prediction first, and then I'll show you a variant of it. It's just based on sample splitting. Again, it goes back about 20 years. So you take your data and you randomly split it into two parts. And I'm going to call these two parts D1 and D2. This is just a random split. They don't have to be equally sized. And in fact, typically they will be unequally sized, in the sense that I would prefer to use most of my data in D1 and save a little bit of data for D2. So if I had 10,000 points, I would put 9,800 points in D1, and I would put maybe 200 points in D2, something of that kind. So it's a random split of the data. And on the first part of the data, D1, that's where I train my predictor. So I run my machine learning algorithm not on all the data, but on most of the data, and I get this prediction A. And then what do I use D2 for? I use D2 to quantify how well I'm doing out of sample. So I calculate some kind of holdout score, or out of sample loss. I'm calling that R here because R stands for residual. But essentially, it's some kind of a loss that tells you how well did A that I trained on D1, how well did it do out of sample? So the holdout part of how well did it do on D2? Okay, so I have some set of points in D2, and each one of those points has some kind of a loss. I'm going to call that set of losses, or the set of residuals, as R bar. So R bar is just a set of each of the residuals. So the residuals are just scalars. It just tells you how well you did out of sample. So a large loss means you did badly. A small loss means you did well. And so you have some set of numbers which just tells you out of sample how well did you do. And what I'm going to do is I'm going to calculate, like, alpha is like, I think of alpha as 0.05. I'm looking for a 95% prediction set. So what I do is I summarize R bar with a single number, which is the 1 minus alpha quantile of R bar. And if you're not used to thinking about quantiles, I just mean that I sort R bar, I just sort the vector, and I pick the 95th percentile element. So the 95th largest element. If I have 100 elements, I pick the 95th largest element. And that's what I'm calling Q1 minus alpha of R bar. And then the prediction set that I form is very simple. It's on my new point xn plus 1. Remember, xn plus 1, I'm trying to predict yn plus 1, and I'm producing a set for that. So what I do is I keep all the values little y, for which when I pretend as if little y was the true label, and I calculate the residual. So that's, this residual of xn plus 1 and little y. I calculate that residual. It's smaller than this 1 minus alpha quantile of r bar. Okay, so the algorithm A comes from D1, the 1 minus alpha quantile of R bar comes from D2, and then I just pick every little y that satisfies this constraint. And the amazing theorem is that without any further assumptions about what the algorithm is or what the underlying data is, the probability that yn plus 1 lies in this set is actually at least 1 minus alpha. This really does give you a 1 minus alpha prediction set. And it's not loose in the sense that you can actually prove an upper bound that it's also at most 1 minus alpha plus 1 over n2 is the size of d2. So like up to a small discretization error, you really do get 1 minus alpha coverage as long as your residuals are distinct. So meaning if every residual was 0, then you don't get that. But if the residuals are distinct, which typically they will be, you get pretty much exactly 1 minus alpha coverage. So very simple method. Here's an example with a particular choice of residual. So how you define residual is up to you. Maybe the simplest form of residual is just y minus a of x. It's like just like the usual least squares type of residual. But a more interesting type of residual actually involves quantile regression. So this is from a 2019 paper which defined a CQR method. It's called conformalized quantile regression. And so here the instead of training one algorithm A, I actually trained two algorithms A. They're basically a quantile regression at level alpha by 2 and a quantile regression at level 1 minus alpha by 2. And then I train both of them on D1, and then on D2 I calculate these residuals that are defined on this slide, which calculate like somehow tell you are you less than the alpha by 2 quantile, or are you greater than the 1 minus alpha by 2 quantile, or are you in between them? So that's roughly kind of what this residual is trying to capture. And then when you push this through conformal prediction, you get prediction sets that look like the first figure, the figure on the left. I would actually ignore the figure on the right for the moment, but the figure on the left shows again just univariate data for visualization. X is on the x-axis, and here y is one-sided, which means that there's very little noise on the negative side, and there's a lot of noise on the positive side. So it's one-sided, heavy-tailed noise. And what you can see is that conformal prediction kind of adapts to this quite nicely. And on the lower confidence bound of the prediction intervals, it always says basically 0. It says pretty much all the time I can predict 0 as my lower bound, and that's fine. But on the upper side, I have heteroscedastic noise, which means that the noise varies with x, and the prediction band or the prediction intervals actually that you get at each point vary in length, automatically adapting to the level of noise. So when x is near 0, there's very little noise, so the band is like the interval is narrow. When x is near 1.5 or near 5, the noise is quite large, so the band is automatically larger. Now, we didn't need to know any of this. Conformal prediction figured this out from the data. So like automatically by running conformal prediction with this choice of residuals, you get out prediction bands that are adaptive in some sense to the underlying data. And so these things tend to work pretty well in practice. I said most of the talk I'll focus on regression, but just to show you an example of classification here, here on the top, I'm showing you an example with 3-class classification. So the data is actually just coming from a mixture of 3 classes. So a mixture of 3 Gaussians in this case. Class 1 is the yellow class, class 2 is the blue class, and class 3 is the orange class. So I have raw data, and right now this is 2-dimensional data. So in this plot, you're actually seeing the raw 2-dimensional data, and the class labels are only in color. And what you're seeing in the first plot is what conformal prediction gives you when you choose a particular choice of residual. So this residual function in this case, I've written it on the top right. You don't have to parse it, but it's roughly the total probability of labels that your classifier deemed to be more likely than the true label. So there's just some measure of quality of your classifier. And when you plug that in through conformal prediction, it produces these very sensible prediction sets. So for example, in the very middle of the plot, you see that the prediction set is actually 1, 2, and 3. It's confused between all 3 labels. On the corners, it knows the set. So like say it's like on the left corner, it knows that's label 1. In the bottom right corner, it knows that's label 2, and so on. And then like if you look between class 1 and 2, it's perfectly, the kind of, it's confused only between those two classes and not for the third class and so on. So it really is giving you like here the colors are showing if the test point lie in that region, then what would the uncertainty set have looked like. So you should imagine the test point, if it lays somewhere here, then this is kind of the colors show you what conformal prediction will predict in those regions. The lower plot is just a the same thing but in a two-class scenario. So here the data is two-dimensional but just a mixture of two Gaussians. And when you push this through conformal prediction, it says, well, if you're on the left, I know you're class 0. If you're on the right, I know you're class 1. And if you're in the middle, I'm not sure. So I'm going to say 0 and 1. I'm going to say both of them. And so there's some region over there where it's confused between the two classes. And so the very kind of works well out of the box and has a rigorous mathematical guarantee that really these are 95% prediction sets for the unknown label. Now, if you don't like the sample splitting idea, like you're like, you don't want to keep some of the samples aside for calibration, there's a leave one out version of this. I'm not going to describe it in great detail, but the idea is very simple, like just like standard leave one out methods. They're only scalable if, if you're willing to retrain your algorithm many times, each time leaving one data point out. So here, originally, instead of training just one predictor, here you train n predictors, each time on a subset of the data that drops one of the data points. And you calculate your standard kind of leave one out scores on the data point that predictor didn't see. You calculate the loss on that score. And then the jackknife plus method, which was an annals of statistics paper by a group a couple of years ago, gives a very simple formula for how to construct a prediction set that combines all of these n predictors and these n leave one out scores into a single interval, that without any distributional assumptions or without knowing any details about what the algorithm is doing, it has in this case a 1 minus 2 alpha coverage guarantee. And the clean thing about this is that if your algorithm is really good for the data, which means suppose your data is simple and your algorithm works well, then these residuals will be smaller, the 1 minus alpha quantile will be smaller, and the set you get will be smaller. But if you used a very bad algorithm or the distribution of the data is very difficult, then automatically the held out residuals will be larger and the constructed prediction sets will be larger. So somehow conformal prediction doesn't need to know any of the details about how about the distribution of the algorithm, because it just learns the performance on held out data and figures out the prediction set using that. Now we want to take this to the settings of distribution, shift, and drift. And so there's three types of distribution, shift, and drift that people typically talk about in the literature. So one of them is called covariate shift. So here the distribution of x changes, but the distribution of y given x does not change. And so in a NeurIPS 2019 paper, we kind of handled that case. The other setting is called label shift, which is the distribution of y changes, but the distribution of x given y does not change. And so in a UAI paper, we tackled that case. For this talk, I'm not going to assume a particular form of the shift. The distribution can shift somehow, and you have no idea. It could be a mixture of covariate and label shift. It could be just, it could be anything, and you don't know what it is. And so our most recent paper handles this case of general distribution, shift, and drift, and that's what I'll describe next. Okay, so the setting actually over here in what follows is actually 100% assumption free, which means that earlier what I just showed you, conformal prediction has very, very weak assumptions. It actually uses just that the data is i.i.d and that the algorithm is symmetric. But now going forward, we're going to drop those two assumptions also. There's going to be no assumptions on the distributions. We're not going to assume they're even independent nor identically distributed. And same with the algorithms. They can treat the points asymmetrically. And I'll show you, there's of course no free lunch. I'll show you what the theorem looks like. But the method of conformal prediction is generalized, and the resulting coverage that you get is going to be analyzed. I'm going to sketch the algorithm and leave the details to the paper. Now, to introduce our generalized conformal prediction algorithm, I need a little bit of notation, and that notation is weights and tags. These are very kind of natural notions, so it shouldn't be very difficult. Now, every point is going to be assigned a weight. You should think about this weight as roughly how important that point is to you. So Wn plus 1 is always going to be 1. And Wi for any of the other training data points is some number between 0 and 1. Okay, so just some, but there's no assumptions on this weight. It's not a likelihood ratio or something of that kind. We don't need that weight to actually have any property. Okay, so these are just some fixed weights, and you'll see how we would set them in practice. And then I'm going to call W tilde I as the normalized weights. Okay, so I take all the weights, I add them up and I normalize them so that they sum to 1. Okay, so that's W tilde I. Okay, so we have weights for every point. Every point is also going to be assigned a tag. So a tag is simply an identifier so that the algorithm can actually treat those points differently. So the tag could be the time at which you observe the point. It could be a spatial location of a point, or even just the index of that point. So essentially now we allow the algorithm to use to differentiate between different points by just saying, well, not only do you have covariates, but you also have this tag that could, if it wants, uniquely identify a point. And so the algorithms could use this tag information differently. This is just a way of saying that we allow for asymmetric algorithms. Okay, so the method of the generalized conformal prediction is very simple. It actually just involves a random tag swap and using weighted residuals instead of residuals. Okay, so the first step is actually I pick a random index k out of the n plus 1 points with probability w tilde I. Okay, so these w tilde i's were my normalized weights. I draw a random index k. Now what I do is I actually swap, or I actually imagine running my ML training algorithm with the n plus first tag swapped between the kth point and n plus first point. So essentially, um, uh, I have my tagged data xi, yi, and ti, but two of the data points have a wrong tag. So xk, yk, where k is a random index, has the n plus first tag, and xn plus 1, yn plus 1. I don't know yn plus 1, of course, but I have a guess for it, for example. That has the kth tag. So I'm actually going to apply my machine learning algorithm, which deals with the data points asymmetrically, but I'm going to apply it to effectively this one random tag swap data. And then I'm going to calculate residuals. I didn't explain what's called full conformal prediction, but you can use split conformal, jackknife plus, or full conformal. We have all three variants in the paper, and we get these types of residuals from the data. This Ri superscript y means the residual where I guess that yn, I don't know yn plus 1, so I guess it to be little y. And so I have residuals with this data set with little y plugged in there. And the set that we construct is very much like the set you saw before. It's the set of all y for which the n plus first residual is less than the 1 minus alpha quantile now of not the simple empirical distribution of residuals, but some kind of a weighted empirical distribution of residuals. So earlier you can view what we were doing earlier, where all the weights were 1, and we just take the 1 minus alpha quantile of the empirical distribution of residuals. Now I just have some weighted version of that. So the red, what's in red font is a minor variant of conformal prediction, and that's the method. So the method is just do a random tag swap according to the weights and then output this weighted residual based conformal set. Okay, so that's the method. I mean, again, maybe it's not so obvious why this should do anything good, and I'll leave the details to the paper. My maybe point here is it's very simple. It's if you know how to do conformal prediction, it's very simple to adapt the methods to this setting. So here's the main theorem, and I won't try to go into too much technical detail, but it's worth pointing out what result we have on the matter. So Z is just going to denote the full data set. Zi is just xi, yi, and Z is just Z1 to Zn plus 1, like all of your data. And Z superscript I is the data set you get by swapping the n plus first point and the ith point. Remember that now I'm not assuming that my data is i.i.d or anything, even independent. So actually my data could be dependent. It could be a time series also. So swapping I and n plus 1 actually does change the joint distribution of the data. Okay, and so and finally R, as we've seen before, R is this residuals when the algorithm is fed in Z. Now, our non-exchangeable conformal prediction has no assumptions at all. So the theorem statement, this just holds under no assumptions on what the data is or what the algorithm is. The coverage guarantee that we get, so we have an upper bound, but I'll skip the upper bound. Just let's focus on the lower bound. The probability that yn plus 1 lies in our set is at least 1 minus alpha minus some kind of price that you get for deviating from exchangeability. So what you should think of this as, this is DTV is the total variation distance. It's like a distance between distributions of the residual applied to Z and the residual applied to Z with the ith point swapped with the n plus first point. And these total variation distances are weighted by W tilde I. So the game is going to be that in practice, if you know, for example, that some points are closer in distribution to your test point, you want to give them a higher weight so that when DTV is small, those points have a high weight. And when DTV is large, those points have a low weight, so that the price you pay for deviating from exchangeability is very small. So this is kind of an oracle result, and it works for our algorithm, and we can get the same type of bounds for split conformal, jackknife plus, things of that kind. And there's a few remarks. As I mentioned, this really does generalize conformal prediction. If you given every tag being identical, if you just put all the tags as 0, you get back a symmetric algorithm. And so the corollary of this theorem, what this theorem implies, is that classical conformal prediction itself with symmetric algorithms, if you use weighted residuals, it's actually robust. If you use identical tags and equal weights, then you actually just get back the classical conformal prediction algorithm. Because if you have the same tag and you do a tag swap, you swapped a tag of 1 with a tag of 1, it doesn't change anything. And if you don't use weighted residuals and you have equal weights, you get back the unweighted empirical distribution. And so what the theorem tells you is, how does classical conformal prediction do if we don't assume exchangeability? Without any assumptions on the data, the theorem tells you exactly how much you should expect a loss in coverage. The third corollary, of course, is if the data is exchangeable, there's actually no loss in coverage. So, which means that the total variation distance, that term that you saw on the previous slide in the theorem, that's actually 0, and you actually just get 1 minus alpha. So the kind of the takeaway message is that if your data is actually exchangeable, using tags and weights don't actually hurt coverage. Like treating the points asymmetrically and using weighted residual distributions, it actually doesn't hurt coverage if you have exchangeable data. And the hope is that they help with coverage if you have non-exchangeable data. The fourth remark is that if you are in a setting with distribution drift, which means your distribution is drifting slowly over time, which means your n plus first point is actually more similar to your nth point than to your first point, then what you should do is you should pick a decreasing set of weights, which means 1, the n plus first weight is the largest, and then n is the next largest, and then n minus 1, and so on. This is very natural. If you're a time series person, this is exactly what you would do. You would pick a decreasing set of weights, maybe even exponentially decreasing set of weights. And this is and what happens is that close by points which are similar get high weights, and then far away points get low weights, and then the loss in coverage term is actually small. And maybe the last remark I want to make is that the total variation distance between the points doesn't matter, but only between the residuals. So if the distribution actually shifts in irrelevant features and the algorithm happens to ignore them, for example, you're running the lasso and it ignores irrelevant features in which the distribution has shifted, then actually you get no loss in coverage at all. And so the theory does actually say something quite non-trivial in that case. Okay, so here's a sanity check empirically on some i.i.d data. Okay, so here I'm just getting to simulations. We're going to generate data from a linear model. So yn is just xn transpose beta plus some Gaussian noise, and xn is itself spherically distributed. And so at time n, we have seen the first n minus 1 points. Then we see xn, and we need to produce a prediction interval for yn. Then we observe yn, and we can check if it's covered or not. And then we move to the next point. We observe xn plus 1. And then we have to make a prediction interval for yn plus 1. And then we observe yn plus 1, and we can check if we covered or not. And the key thing to take away over here is that CP stands for conformal prediction. Next CP is non-exchangeable conformal prediction, which is our method. LS is least squares. WLS is weighted least squares, where I weight the older points less, and I weight the more recent points more. And the takeaway message, what you're seeing over here on the left is coverage, and I'm aiming for 95% coverage. And the right is width, like how wide are the intervals. And what these plots are saying is that our non-exchangeable conformal prediction method doesn't really face any loss when you actually when your data happen to be i.i.d. You're using weights, you're using tags, you're doing this something slightly more sophisticated, but you're not really paying a price under the i.i.d setting. You're basically just kind of getting back conformal predictions performance. Okay, so that's like a sanity check that it's doing something sensible. It is getting 95% coverage over time. So the x-axis is time, and as you're going across time, you are really covering 95% of the time. The second sanity check is what happens in a sharp distribution drift. So what I'm now showing is now there are two very sharp change points at time 500 and at time 1500. And so it's still a linear model, but beta n is kind of constant for the first 500 steps, and then it changes drastically. And then it's constant from between time 500 and 1500, and then it again changes drastically. And so obviously, exactly after the change point, there's no hope. I mean, the distribution has drifted hugely and you have not seen any data, so you can't expect to have good coverage. So all the methods, their coverage, which is on the left plot is coverage, the coverage is good before time 500 because it's i.i.d. data. But then immediately at time 500, all of them, their coverage drops. But non-exchangeable conformal prediction, the coverage like kind of it comes back up quite sharply. Like very quickly you kind of learn that the old data is to be ignored, and and so you're able to use these weights sensibly, and you kind of quickly get back to nominal coverage. And this is kind of as good as you can expect. And then you get back to 95% coverage till the like between times like 900 and 1500, you get exactly 95% coverage again. You don't overcover, things like that. And then again, there's another change point at 1500. Again, your coverage drops, but then very quickly it kind of settles back down to about 95%. So it's doing something sensible on the left-hand side with respect to coverage. It's really giving us 95% modulo these blips. And on the right, you're seeing the prediction interval width. And the green curve is non-exchangeable conformal prediction with weighted least squares. So what you're really seeing is that using these weights that decay, as opposed to just using least squares, really does help. Naturally, because least squares treats all the data kind of equally well, and weighted least squares, kind of forgets the past eventually. And so that's kind of what you should be doing in the setting. So it's no surprise that you get shorter intervals. And so the key idea is that both the using of the tags and the using of the weights both help. They both help with coverage as well as getting short intervals. The third case is of slow distribution drift. So here in this case, beta n is changing at every step. So it's continuously changing a little bit at every step. And what you see on the left is our non-exchangeable conformal prediction methods work perfectly. They just they're able to constantly adapt, and they keep getting 95% coverage. While if you just ran conformal prediction, it of course it's not going to do well because it treats the data exchangeably, but it isn't. The distribution is drifting. And on the right, you see that when you use weighted least squares with NextCP, it's also keeping the width kind of constant. So really, it's really like learning the model. And here, the right thing to do, somehow the right width is kind of related to the noise level. In this case, it's standard Gaussian noise. And so the width should be, let's say, 1.96 into 2 or something of that. And that's kind of what you should expect. And that's kind of what you see here. So it all makes sense in a variety of simulations. Now, let me show you a real data example from electricity forecasting. Here, the data is from from Australia, between New South Wales and Victoria. It's a data over 3 years from 1996 to 99, and there's electricity usage and pricing every 30 minutes. So the covariates here are the demand in New South Wales and Victoria, and the price in New South Wales and Victoria. And the response, the thing we're trying to predict, is how much electricity was transferred between New South Wales and Victoria in the following 30 minutes. So at each time step t, we first produce a prediction interval for how much electricity we think will be transferred. Then we observe yt, and we know whether we covered or not. And then we see the next set of covariates, and we make another prediction interval, and so on. So you're doing this sequentially over time. And kind of what you see on again, the left hand is coverage, the right hand side is interval width. The green curve, again, the non-exchangeable conformal prediction really does well. Like it really does get you 95%. This is really non-exchangeable real data. We have, there's all kinds of weird shifts in the data, because you can see that conformal prediction, its coverage sometimes goes below almost to 60%, and then it shoots up to near 1. So conformal prediction is suffering from the fact that this data is hugely time varying. But our new methods seem to really get you 95% coverage. And if you look at the widths, they're quite reasonable too. I mean, there are some points in time where you have to be a bit wider to get coverage, and there's other points in time where you can be narrow and still get coverage, and they seem to kind of adapt automatically to that. So again, so it seems to work well kind of in all of these settings. I'm not going to get into the detail. We also, in the paper, we also looked at an example of election forecasting where, we have some data from the green counties in the US, and we're trying to make predictions about the rest of the US. Obviously, the distribution is very different from the green data and the rest of the data, but we can use 2016 covariate information to talk about how similar counties are and assign weights and things of that kind. And, it does reasonably well in practice. Okay. In the interest of time, I'll just tell you a little bit, maybe 7-8 minutes about calibration, because I think it's an important topic. Now, I call this so in an earlier paper of ours from NeurIPS, we think of uncertainty quantification as being a tripod. There's 3 kind of definitions you could choose for how you want to quantify your uncertainty. So the first one, which we covered, is a prediction set. You're trying to cover the unknown label with high probability. Another option is something like a confidence interval. Like, for example, if y is real valued or binary, you can say, I want a confidence interval, but for what? For example, for the conditional mean of y given x, you could do that. And it turns out that, so there's some subtleties where that's actually a difficult problem to do without making distributional assumptions. But a third one, which I will talk about briefly now, is called calibration. And in calibration, it makes most sense in the classification setting. I'm going to talk about binary classification briefly. Is you want to produce a prediction f of xn such or f of xn plus 1 such that the expected value of yn plus 1 given your prediction is approximately your prediction. So that's the definition of calibration. And again, briefly, at a very high level, we have a new result called online flat scaling, which shows how to recalibrate classifiers online on the fly that adapts really well to distribution shift and drift. Okay, so what is calibration again? Like this notion of calibration is classifier f is called calibrated if the expected value of the true label given the prediction actually equals the prediction. And what does that mean? It means that suppose we make the prediction of, let's say, 0.3. On 100 different points, we predict 0.3. If about 30 of those points had label 1 and the rest of them had label 0, then we are calibrated. But if 50 of them had label 1 and 50 of them had label 0, then we're not calibrated. We should have said 0.5, but we said 0.3 instead. Okay, so calibration is like a very sensible and kind of baseline notion. But of course, in reality, exact calibration is impossible with a finite sample data. And typically, trained classifiers are not going to be automatically calibrated. If you have a deep learning algorithm, it's not going to be calibrated out of the box. So what you want is a post hoc calibration method that kind of takes in an algorithm like a deep learner and some additional data set like a calibration data set, and it spits out an F that is at least approximately calibrated. So you take in a classifier and a data set and you output something that's approximately calibrated. And what do you mean by approximately calibrated? We say that this method is epsilon alpha calibrated if you're not going to get exact equality, but if the difference between the left hand side and the right hand side in the first equation, if that difference, the probability that that's greater than epsilon is at most alpha. So epsilon and alpha are just simply like some small constants like 0.01 or something like that. And you say, well, I'm okay with tolerating some small differences which occur with some low probability. That's okay. So the rough takeaway message is that post hoc calibration of probabilistic classifiers for i.i.d. data can be accomplished in a distribution-free fashion by a simple binning algorithm. It is also possible to produce calibrated predictions against adversarial realities using some techniques in online learning. And in recent work, we kind of unified and generalized both of these techniques and developed a method that works well under distribution drift or shift and is kind of robust against adversarial data as well. So I won't tell you about the binning-based method. Like maybe you can check my slides out later on. But let me tell you briefly in a few minutes about online flat scaling and calibrating, which is an ICML paper that's going to be presented in a couple of months. So what is flat scaling? It's very simple. It says that instead of outputting f of x, which is what your probabilistic prediction would have been, I just transform it using two constants. Okay, so essentially what I'm going to output is m of f of x. I'm going to just transform f of x. And m is just given by these two constants a and b. I'm going to multiply the logit of f of x by a and add b. And essentially that's what flat scaling does. So it essentially looks like take your probability and just adjust it a little bit. And what online flat scaling is, I won't go into the details of the algorithm, is it has two like new pieces. We replace the logistic regression in flat scaling by online logistic regression, which is a problem studied in online learning. And we couple it with something called calibrating so that even if the data is completely adversarial, you actually still have a calibration guarantee. So we end up proving like a best of both worlds kind of setting where like, you start with some pre-trained machine learning model, you kind of post hoc calibrate it using online logistic regression, and you calibrate it to protect it against adversarial data. And now this method works well on i.i.d. data, it works well on adversarial data, it works well on distribution shifts and so on. So that's kind of roughly like what online flat scaling is doing. You should think about it as what we did for non-exchangeable conformal prediction. We want to develop those types of ideas, but for the calibration literature. Now, I know we're like at 2 o'clock, but I wanted to ask Sebastian if I can take a few minutes to go through only a simulation, like just no more theory or anything, like just a simulation slide. Would that be fine?
You can take 2 minutes.
Okay, I'll take 2 more minutes. Thank you. Okay, so here's the example that I would just like to describe. So here again, x is one-dimensional, and y, the probability of y given x is on the x-axis. So I'm drawing data from this model. The yellow curve is actually the true probability. I mean, it's a simulation, so I can set the probability of y given x how I want. That's the true probability. The gray bars are the data that you're actually seeing, and in this case, the data is mostly between, like the training data is mostly between like -5 and 10. That's where most of the data is. So when you train a logistic regression classifier on that data, it does really well over there. So for example, the blue dotted curve is a learned logistic regression model, which is very accurate around the gray histogram. Where you have data, it's accurate. But if you look to the right of the plot, it's extrapolating quite badly. In regions of X where you haven't seen much data, it actually kind of contradicts the real model because it has no data to know what the real model is like. Now, what happens is we run our online flat scaling algorithm on this type of data and allow the distribution to drift over time. So what you're seeing in the bottom plots is the gray histogram of X is actually now shifting rightwards. And slowly you're entering regions of the space where you've never seen any training data, and your test data is actually coming from completely new regions. And what the online flat scaling method does, it takes this fixed base model in blue dotted curve, which is completely wrong on the right half of the plot, and it fixes that. And especially the last plot is really interesting because it shows that it realizes that between when x is between 20 and 30, the base model in blue dotted curve, it completely contradicts the true model, meaning it's like exactly opposite of the true model. And the online flat scaling algorithm is able to realize that and flip the prediction. So the red, dashed curve that comes out of online flat scaling is actually like it fixes the base model to actually match the truth. And it does this in a kind of fully online fashion, never retraining the fixed model, but only running like our online flat scaling on top of it. So I think with that, I've at least hopefully given you, I knew I'd run out of time and I'd only give you a glimpse of it. But if you're interested, please check out the online flat scaling paper. It's on arXiv and it will appear in ICML. But I think there's much more work to be done on both of these problems. And maybe I'll stop here and see if there are any questions.
Thank you very much, Aditya. Est-ce qu'il y a des questions? Are there any questions? Okay, I will start with one question. So you said that in the case of exchangeable data, you keep coverage. But I guess that taking non-uniform weights affects utility, right? Efficiency of the length of the intervals. So a natural question is, can you learn the weights so that you can adjust to the non-exchangeability of the data?
Yeah, absolutely. That's a great question. And I think the answer is rough. Yes, in practice, but I'm not sure in theory. So in practice, what I would do is on older data, treat the weights as if you think that your data is roughly stationary and you think that weights in like on older data are going to be roughly good even today, so it's roughly stationary, then yeah, I would actually treat the weights as parameters that I can try to learn and see what set of weights kind of maybe, for example, I would have the weights be exponentially decaying, but I would tune the exponent on some past data. And then on the current step, I would use that tuned exponent. I would do something like that in practice, but it's very hard to show that that works theoretically.
I see. Thanks. Are there other questions? We get some.
Thank you for the talk. In sequential learning, there are methods, for instance, upper confidence band, where you will choose the X with, for instance, the largest quantile, and there you will query a new output corresponding to this X. And with this, under some assumptions, you have a convergence rate. For instance, if you just want to maximize the conditional expectation in regression. And then do you think with the current results on conformal inference, there could be these types of results?
Oh, that's a great question. Okay, so I mean, I should point out over here I mean, in the setting you pointed out, the distribution of X is I mean, in a banded setup, let's say you choose which points vary, and here, of course, we don't know anything about the distribution of X. But a key point is you can only construct upper confidence bounds if you know something about the distribution of Y given of the noise. So if the noise is nice, sub-Gaussian or something of that kind, you can. But actually, if you notice, we made no assumptions on the distribution of the noise either. So there's some subtleties over there, whether like, you really can cover quantities in such that the let's say the width of the the interval that covers the conditional mean can vanish. And it turns out that if you're in a distribution free setting, we are allowed to have absurdly heavy tailed data, even Cauchy data, something of the Cauchy noise. In that setting, you can have settings where you can cover y, like using conformal prediction, but you cannot cover the expected value of y given x, meaning there's no interval that can shrink to zero as you get more data. But I think there is something interesting to be said at the intersection, which is when you are querying x, can you use conformal prediction intervals to guide the exploration as opposed to using upper confidence bounds algorithms for the conditional mean of y given x? So I think that there might be something over there. I'm not sure that if that fully answered your question, but yeah, you can clarify if it did or not. Yeah.
No, I think you answered my questions very well.
Okay. Yeah. Thank you.
Many thanks.
So we have one more question. The mic is arriving.
Thank you for the talk. I would like to know, how do you actually measure the quality of your conformal predictions? Like, is it the length of the intervals only? And if that's the case, like if you have two same intervals of same length or with two methods, how do you actually measure which one is better than the other?
Yeah, I mean, I think for all of these plots, including in I guess in real data, we're looking at both things, coverage and length. So I mean, I think conformal prediction, the baseline is you should get coverage, and I mean that of course is very challenging under settings with distribution shift and drift. But then if you have the right coverage, then I can look at the length of your interval. So I would say, I mean, that's usually the case, that we go for coverage first and length later. But there isn't any clean way to compare completely. I mean, in the case of real value regression, I mean, interval length makes sense. But if my thing y that I'm predicting is actually multivariate, and I have a prediction set, then it's not clear how to measure, how to compare volumes of prediction sets. Like if I have one is more spherical and one is an ellipsoid, what's the right way to be comparing them? I mean, I guess volume, but I don't think we have a way to optimize that or find kind of a method that's optimal. And the reason is there's so little structure or assumptions in the setup of the problem. If you assume more about the problem, for example, additive noise and it's light-tailed, then you can get methods that are kind of oracle optimal, which means we know like if you were God, or if you were an oracle or whatever, like the underlying distribution, the right thing to do is predict using the conditional distribution of y given x. So taking like a level set of the conditional distribution of y given x is what an oracle would do. And we can try to see if conformal prediction manages to mimic that under certain specific structural settings, and often it does.
So we have time for one more question, if any. So no, so we will just present the next the content of a session, the next speakers. Thanks again, Aaditya, for the talk.
Thank you very much. Thank you.